Bismillah ar-Rahman ar-Rahim. Welcome to lecture number 25, Theory of Automata. We will discuss finite automata with outputs. This is the outline of today's lecture. We will revise our previous lecture. In previous lecture, we talked about some quizzes. We will provide solution to those quizzes, and then you can compare your solution to the solution I provide. So in case there are some mistakes, you can fix these. And then we will continue the discussion to discuss a new type of machine which is called finite automata with output. Okay, so in last lecture there was a quiz and it was determine the regular expression for the NFA with null string. So this is NFA with null string, and what we have to do, we have to determine the let me create a pen. We have to determine the regular expression for this language. So this is the solution. This is we have NFA with null string, and if we convert it to regular expression, so what we do, we try to eliminate this state. So when we eliminate this state, so you see 2 and 3 they stay as it is, but when we eliminate, so you see there is path. Okay, so one path is this one, and the other path is this one. So for the one path, so lambda is here, lambda, and for this path a star a, we have added this one here, and b a star a, we added here. Okay, so try to revise the previous lecture and try to understand how we eliminate states. I just explained it. Okay, so we eliminated only one state. Now let's try to eliminate state number 2. And I think state number 2 is there are two paths. One path is this one, and the other path is this one. So I think it will become like this. From 3 to 4, you see, from 3 to 4 and from 1 to 4, there is a path. 1 to 4 and from 3 to 4. 3 to 4 it is A concatenated with this, and 1 to 4 it's A concatenated with this. Now let's try to eliminate state number 3. So eliminating state number 3, we have one this path and then two these paths. So we can basically combine these two paths by adding a plus sign here. So it will be this one by combining these two, right? So these two, and then it is in the same direction, so we concatenated it here. Okay, and then you see there will be two paths from 1 to 4, so we can combine those two like this by adding a plus sign. And basically we can no, we cannot remove lambda, so we will leave it as it is, and this will be regular expression like this. which can be further reduced to this one. How do we reduce it? So A concatenated with lambda is A. A concatenated with this string, it becomes A, and this one, and then lambda plus B, it becomes as B. So B concatenated with A, sorry, so it's B A star A. It is this one, B A star A. And then we have BA. So in case we take this path, so this is BA. And in case we take this path, BAA. So it will become like this. And in case, well, it's this one here. This is like this. So in case we take this path and we take this path, so it will be like this. And here we can see there is something common. B A star A plus BA is equal to B star A. So this is reduced like this. So this eventually it become regular expression like this. So you see, it's not always easy to convert FA to regular expression, but you have to pay attention to all the detail of the machine, and then eventually, because this is just an algorithm that you follow, and with that algorithm eventually you get regular expression. There was another quiz. Build an FA corresponding to the given NFA. And this is NFA. You see, there are no transition on this state, and we have to build FA. This is the regular expression of this language. And what we can do, so we have this state 2 and 1. So at 1 reading B and at 2 reading B, we end up in this state. And in both state reading A, we go there. So basically we have to build FA that accepts FAS that accept double B. But the other states are coming because we have to deal with all the transitions. Basically it can be reduced further. We can have only one final state. So in this we are following the algorithm, the combination 1, 1, 2, 1, 2, 3 and 1, 3. So this is the FA we have. Using FAs corresponding to these two regular expressions, build an NFA corresponding to R1 union R2. So this was the two FAs that are given, and we have to build FA of R1 plus R2. And this was easy, like we created new state, and for these states we create A and B and A and B. So NFA equaling to FA1 union FA2 is given as this one. This is basically the corresponding regular expression. Now build an NFA for FA star. So this is the regular expression for this language. And this is the NFA for FA star. We create a new start and final state. We connect it with transition B and A. So here on B we are at state 1, and here on transition A we are at state 2, and the other transitions are basically not changed. Now let's see a quiz. This was another quiz I gave you, and you have to build NFA for FA star. So this is initial and final state. This is 0, this is 1, and for the final state we make sure that we create any combination of this string. So this is NFA for FA star. Now in all these lectures we talk about different types of FA. We talk about FA, we talk about TG, we talk about GTG, we talk about NFA, we talk about NFA with epsilon. And all these machines, they accept regular languages. They try to process some strings, but they do not produce any letter as output. So here we are going to study a new type of machine which is called finite automaton with output. So FA is discussed so far is just associated with the regular expression or the language. Now there is a question, does there exist an FA which generates an output string corresponding to each input string? And the answer to this question is yes. And these machines are called machines with output or FA with output. Basically, there are two types of machines with output: Moore machine and Mealy machine. Let's try to discuss Moore machine. A Moore machine is a collection of 5 things: a finite set of states. These states can be labeled as Q0, Q1, Q2, and so on, where Q0 is the initial state. So we have the same as initial state as in FA. Now an alphabet of letters ABC represented by sigma, from which the input strings are formed. So this one and this one, this is new. An alphabet, this is another sigma of XYZ. These are labeled with the beginning alphabets and these are labeled with the last alphabets. Of output characters from which output strings are generated. A transition table that shows for each state and each input letter what state is entered the next. And this is new, an output table that shows what character is printed by each state as it is entered. Since in Moore machine no state is designated to be a final state, so there is no question of accepting any language by Moore machine. Moreover, the state to be initial is not important, as if the machine is used several times and restarted after some time, the machine will be started from the state where it was left off. So being initial state is not important. We start from initial state, but it's not important. So let's take an example. Consider the Moore machine having states Q0, Q1, Q2, Q3, where Q0 is the start state and alphabet is AB, and output letters are 0, 1, and the transition table is given as. So Q0, which is initial, Q1, Q2, Q3, and new state after reading A are B. So when we are at Q0, and when we go from Q0 to Q1 or Q3, what we print? We print A. We print 1. From Q1 reading A, we end up at Q3 and we print a letter 0. From Q1 reading B, we end up at Q1 and we print a 0. From Q2 reading A, we go to Q0 and we print 1. From Q2 reading B, we go to Q3 and we print 1. Okay, so these output characters are associated with states. It is given like this. So you see, from Q0, if we read A, we go to Q1, right? And this one, it is here. Okay, and from Q0 reading B, we go here, right? And this one is here. From Q1, this is 0, and we go to Q3, Q1. So this is A, Q3. And on B, reading B, I don't know why transition B is not shown. So Q1 reading B, we should go to Q1. Yes, it is here. It's a mistake. It's a B. Q2 reading A, we go to Q0. Q2 reading A, we go to Q0. Q2 reading B, we go to Q3. Q3 reading A, we go to Q3. Q3 reading B, we go to this one. And their corresponding letters are given here and here. So let's say we have the string A, B, A, B. So if we process it, so we will come from here to A, and what we will print? 1 here, this one. And when we go from A to this one, we will print a 0. And then we read a B, and we end up in a new state Q1, and we print a 0. Then we print an A, right? So we print 1 and a B, and we print 0. So input string is AB, AB, and the output string is 1, 0, 0, 1, 0. So the length of output string is 1 more than that of input string, as the initial state prints out an extra character 1 before reading input. You see, its length is 4 and its length is 5. Why? Because we start from this state. It can be determined by the following table as well. So our input is AB, AB, and we are in state Q1. When we are in state Q1, we read A, we end up at Q1 and Q0, so we print 1. When we read A, we go to 0, we print 0. Then reading B, we go to Q1 and we print a 0. Then we reading A, we go to Q3, we read a 1. Then from Q3 to Q2, the 1. So to know how many times AAB occurs in a language in a long input string, the move machine will count this for us. So what we have to do, we are counting A, and B. And you see we are printing 0, 0, 0. But every time we reach to this Q3 state, we print a 1. So here is a string. B, 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 A, A, B, A, A, B, B, A, A. And we want to know how many times AAB occurs in this string. So what we do? We start from Q0. We print a 0. Then we have a B. So we print another 0. Then we read this B. We print a 0. Then we print this B. We print this 0. Then an A. So we print 0. Another A. We print 0. A B. We print 1. And then an A. This one. We print 0. Another A, 0, and a B, 1. And then we print a B. We follow this path, right? We go to 0. And then an A, we go to 0. And then another A, we go to, I don't know why 0 is missing, but there should be a 0. Now we want to know how many times AAB occur in this string. So just we count the number of A's. Right? So we can build more machine, just one example, to count substrings. There is another type of machine, the same finite automata with output, and it's called Mealy machine. So Mealy machine consists of the following: a finite set of states Q0, Q1, Q2, where Q0 is the initial state, an alphabet of letters sigma consisting of ABC forming the input, an alphabet sigma XYZ of output characters from which output strings are formed, a pictorial representation with states and directed edges labeled by an input letter along with an output character. It's impossible to give transition table in this case. This is very important. A pictorial representation with states and directed edges labeled by an input letter along with an output character. Here is a note. Similar to Moore machine, in Mealy machine, no state is designated to be a final state. So there is no question of accepting any language by Mealy machine. And another note, the state to be initial is not important, as if the machine is used several times and is restarted after some time, the machine will be started from the state where it was left off. Let's take an example. Consider the following Mealy machine having states Q0, Q1, Q2, Q3, where Q0 is equal to start state. Let's say we have input AB, and we have output 0, 1. This is Mealy machine. On Q0 reading A, we output 0 and we go to Q1. At state Q0 reading B, we print 0 and we go to Q3. At Q1 reading B, we print 1 and we go to Q2. At Q1 reading A, we go to 1 and we go to state Q3. At Q2 reading A, we print 0 and we go to Q3. At state Q2 reading B, we go to Q3 and we print a 1. At Q3 reading A, we print 1 and we go to Q3. At Q3 reading B, we print 1 and we go to Q0. So let's say we have input this one. So state by input A, we will go from Q0 to Q1 and what we will print? A 0. Then, so it will be this path. Then we print a B. So we have a B, right? So we will print a 1. And then we will read a B again. And what we will print? 1. And then we will read A. And then we will print 1. And then we have a B. And what we will print? B. We will print a 1. And we have a B again. B again. What we do? We print 0. Then we have B again. And what we will print? We print a 1. And then we have an A. And what we will print? We print 0. So you see the size of the input is the same as the size of the output in Mealy machine. You remember in Moore machine there was one extra character at the beginning. But this Mealy machine is different than Moore machine. Note that in Mealy machine the length of output string is equal to that of input string. Consider an example. Mealy machine having the only state Q0 as the start state. The input letters are 0, 1 and the output letters are 0, 1. And the transition are reading 0, we print 1. Reading 1, we print 0. So our input is 0, 0, 1, 1, 0, 1, 0. So every time we read a 0, what we print? 1. We read a 0, we print a 1. We read a 1, we print 0. We read a 1, we print 0. We read 0, we print 1. We read 0, we print 0. We print 0, we print 1. And if you look, so this is basically the complement of this string. So this particular Mealy machine is known as complementing machine because it complements the input string. Let's take another example. Consider Mealy machine and input letters 0, 1. Output letters are also 0, 1. This is the transition diagram. So from the start state. So these are just start state, overflow, uh, carry, and no carry. So reading 0, what we do? We print a 1. Reading 1, we print a 0. And there will be a case when it is 1, we print 0. If it is 1, we print 0. And then 0, 0, 1, 1. So let's take input. And if you remember this addition, the increment operator, so if we have this input and we add a 1, so it will be 1, and the remaining string remain the same, right? Consider another input. So if you process this one, so 0, 0 will be converted to 1, 1 convert to, so 0 convert to 1, and then it will remain the same. 1 remain the same, 1 1 1 1 0 0 1 0 0 1, right? But if we have this input 1 and we go this direction, so 1 will be converted to 0, and then 1 will be converted to, so this one 0 1 0, and then 0 will be converted to 1, and then 0 0 1 1 1 1 0 0 0 0 1 1. Remember that these strings we are processing from this side, because in mathematics we perform operation this way, right? So make sure that you process this side, not the other side. This machine is also known as incrementing machine. I think we should stop here. Try to understand these two machines, Mealy machine and Moore machine, and we will continue this discussion in next